Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about proof methods and strategies. First, if you're dealing with a statement that's very limited, it might be possible for you to check all possibilities. This is the exhaustive strategy. As an example, suppose we have the following theorem. Every prime less than or equal to 6 is a sum or difference of squares of integers. Well, there aren't very many primes less than or equal to 6. So all we have to check is, in our proof, we have to check 2, 3, and 5. So there are only 3 things to check. How can we express 2, 3, or 5 as either a sum or a difference of squares of integers? Well, 2 is easy. 2 is 1 squared plus 1 squared. 1 squared is 1. 1 plus 1 is 2. How about 3? 3 is 2 squared minus 1 squared. So 2 squared is 4, minus 1 is 3. There's only one more to check. How about 5? 5 is 2 squared plus 1 squared. Right. So that's the end of the proof. We've exhausted all possibilities for primes less than or equal to 6. Here's another example. Prove that n plus 1 cubed is greater than or equal to 3 to the n for integers that are positive, in other words, natural numbers, but we're constraining ourselves to values less than or equal to 4. Because n is less than or equal to 4, in our proof, n lies only in the set 1, 2, 3, and 4. So all we have to do is check that this inequality holds for these 4 values. We should use an exhaustive proof method by just checking every conceivable case. The n equals 1 case. 1 plus 1 cubed is 8. And is that greater than 3 to the power 1, which is 3? Yep. How about that n equals 2 case? 2 plus 1 cubed, 2 plus 1 is 3, cubed is 27. Is that greater than 3 to the power 2, which is 9? Yeah. N equals 3. 3 plus 1 cubed, that's 4 cubed, which is 64. Is that greater than 3 to the power 3, which is 27? Yeah. N equals 4. 4 plus 1 cubed is 5 cubed, which is 125. Is that greater than 3 to the power 4, or 81? And yep, that's true too. So that's the end of the proof. We've checked all possible examples. We next present something by proof by cases. It's based upon the principle that if you have proposition 1 or proposition 2 or proposition n implies q, that's true if and only if it's logically equivalent to proposition 1 implies q and proposition 2 implies q and through proposition n implies q. So a whole bunch of different possibilities. Each of these has to be true in order for these to imply that. You can see this by using some simple basic logic. remember P implies Q is equivalent to not P or Q. It follows then that if I have P1 or P2 or through Pn implies Q, that's logically equivalent to not P1 or P2 or Pn or Q. When we distribute the not through here, we'll get not P1 and not P2 and not Pn or Q, and then we can distribute this and we get not P1 or Q and not P2 or Q and not Pn or Q. And that gives us the conclusion P1 implies Q and P2 implies Q and all the way down to Pn implies Q. So what this means then, if you have a whole bunch of different options that all imply Q, you can prove them one at a time, that P1 implies Q and then P2 implies Q, and so on. So it reduces this one grand theorem into a bunch of different cases. Here's an example. Prove that for integers z, n squared is bigger than or equal to n. There are several cases to consider. There's a principle in mathematics called trichotomy. Every real number is either positive, negative, or zero. There's only those three options. And in our proof, it's pretty easy to see that if n is less than 0, then n squared is bigger than or equal to 0, and that's certainly bigger than or equal to n, which is less than 0. So that checks the negative case. The 0 case is also easy to see. 0 squared is 0, and that is greater than or equal to 0. Yep. How about n positive? That's where the work really occurs. If n is positive, and if n is an integer, then n is bigger than or equal to 1. And since n is positive, you can multiply both sides of this inequality by n, and it maintains the direction of the inequality because n is positive, and that gives you our conclusion that n squared is greater than or equal to n, provided n, of course, is an integer. If we're talking about real numbers, that's a different story. 1/2 squared is 1/4, and that's smaller than 1/2, not bigger than or equal to 1/2. So, but for integers, this will always be true. We broke it into cases because integers include negatives, 0, and positives. Here's another example. Suppose I want to show that the absolute value of xy gives you the same thing as if you take the absolute values of the factors separately. And this is going to be true for all x and y that are elements of R. Again, remember, it's customary to drop the universal quantifier when it's kind of obvious that we're talking about everything. What we'll do is we'll break this into cases, but we'll recall that the absolute value of x is, by definition, x if x is bigger than or equal to 0, and negative x if x is less than 0. So we'll break this into cases as to whether or not x is bigger than or equal to 0 or x is less than 0. And y is bigger than or equal to 0 versus y is less than 0. Since there are two options for each variable, there are going to be 4 cases. So let's do case 1. This is the easy case. Let's assume that these are both bigger than or equal to 0. That means x times y is also bigger than or equal to 0. So the absolute value of x times y will be xy. What does the absolute value do to things that are non-negative? It does nothing to them. And that's also equal to the absolute value of x times the absolute value of y, because the absolute value of x will be x, the absolute value of y will be y, and so that's the end of that case. Let's suppose that they're both negative. If they're both negative, then x times y will be positive. So the absolute value of xy will be xy. But what is the absolute value of x times the absolute value of y? Well, that's going to be negative x times negative y. What does the absolute value do to things that are negative? It outputs the negative of the negative, making it positive. But here we have negative times negative, which is xy. We already know that's equal to the absolute value of xy. And so that's the end of case 2. For case 3, we'll suppose x is bigger than or equal to 0 and y is less than 0. In which case, that implies that xy will be less than or equal to 0. That implies then that the absolute value of xy is negative xy. Also, the absolute value of x will be x, and the absolute value of y will be negative y. So the absolute value of x times the absolute value of y will be x times negative y, or negative xy. And we already know that's equal to the absolute value of xy. That leaves only case 4 to deal with, where x is less than 0 and y is bigger than or equal to 0. So in this case, xy is less than or equal to 0, so the absolute value of xy is negative xy. The absolute value of x will be negative x. The absolute value of y will be y. So the absolute value of x times the absolute value of y is negative x times y, or negative xy, and that's the absolute value of xy. We've exhausted all cases, so the theorem is true. As another example, let's show our no integer solutions to x squared plus 5y squared equals 13. It seems like x and y can't get too big because this sum has to be smaller than or equal to 13. In particular, we can write 13, which is supposed to be x squared plus 5y squared, will be greater than or equal to what happens if I ignore 5y squared. So this puts a bound on x. X squared will be less than or equal to 13. You might recall the absolute value of x is equal to the square root of x squared for real numbers. So note, if we take the square root on both sides of this inequality, we'll have the square root of 13 is greater than or equal to the square root of x squared, which is the absolute value of x. So whatever x is, it can't get too big. And in particular, square root of 13 is less than the square root of 16, which is 4. So that means x must have an absolute value less than 4. That means we're dealing with negative 3, negative 2, negative 1, 0, 1, 2, and 3. So those are the only possible x values that we can have. There are only 7 values to check. And so this shouldn't be too hard to prove. We can do the same kind of analysis for y. We'll have 13, which is equal to this, x squared plus 5y squared. If I ignore x squared, I get something smaller. If we divide by 5, and then take a square root, we'll get the square root of 13/5 is bigger than or equal to the absolute value of y. Remember, we're talking about integer solutions only. 13 divided by 5 is less than 3. Square root of that is going to be bigger than 1 but less than 2. So we'll have to have y values be less than 2 in absolute value. So the only possible y values are -1, 0, and 1. So there are 3 possible values for y and 7 possible values for x. That gives us 7 times 3, or 21 possible values that we need to check. Also note that if you plug in a negative x or a positive x, the negative will get squared away. Same thing for the y's. So technically, you only need to check for the positive or 0 values for both x and y. The negative values will correspond exactly to what happens to the positive values because of the squares. So we really only have to check the following 8 values. If x is 0, y could be 0 or 1. If x is 1, y could be 0 or 1. If x is 2, y could be 0 or 1. And finally, if x is 3, y can be 0 or 1. And so we'll just check these. The 0, 0 case. 0 squared plus 5 0 squared is 0, and that's not 13. So that is not a solution to this equation. 0, 1. 0 squared plus 5 times 1 squared is 5, and that's not 13. 1, 0, that gives us 1 squared plus 5 times 0 squared, which is 1, and that's not 13. How about 1, 1? 1 squared plus 5 times 1 squared is 6, not 13. 2, 0. 2 zeros plus 5 times 0 squared is 4, not 13. 2, 1. 2 squared plus 5 times 1 squared, that's 4 plus 5 is 9, not 13. 3, 0 gives us 3 squared plus 5 times 0 squared, which is 9, not 13. And the only one left, 3 squared plus 5 times 1 squared, is 9 plus 5, which is 14, and that's not 13. So we've checked all possible examples other than the negatives, but they give you the same values because of the squares. And so the theorem is true. Let's do something that's not an exhaustive type proof. Show that if x times y and x plus y are even, we're assuming here that x and y are elements of the set of natural numbers, then both x and y are even. So in our proof, we'll suppose both xy and x plus y are even. What does that mean? It means x times y is 2 times some integer, and x plus y is 2 times an integer. Now we just have to eliminate one variable and try to prove that x is even and y is even as a consequence. Using the process of elimination, we see that y, moving the x over, is 2l minus x. We'll substitute that in up here. We know that x times 2l minus x will be 2k. Now we just need to solve this equation for x and prove that x is even. Distributing x, we get 2lx minus x squared equals 2k. I'm going to get x squared by itself. So I'm going to move some terms around. I'll have x squared is 2lx minus 2k, and note that we can factor a 2 out of that. We know then that x squared is even because it's 2 times another integer. But that implies that x is even. Now that we know that x is even, we can plug that fact back in to show that y is even as well. If x is even, then x is 2 times s, where s is an element of the set of integers. We'll plug that in down here. Y is 2l minus x, which is 2s. We can now factor the 2 out, and that means then that y is even. That's the end of the proof. We've shown both x is even and y is even. Notice that in the course of this proof, we didn't do some exhaustive check for all possible cases. That would have been impossible. What we did instead was we just followed our noses using definitions. What does it mean to be even? And then we combined those. We ended up with a system of 2 equations and 2 unknowns. We manipulated those until we could arrive at the conclusions that we needed. What is wrong with this proof? The theorem is easy enough. If x is an element of the real numbers, then x squared is greater than 0. Note that this theorem is actually false, because if x is equal to 0, 0 squared is 0, and that's not strictly greater than 0. So we know that this theorem is false. But we're asking, what is wrong with the following proof? If x is less than 0, then x squared is greater than 0. If x is greater than 0, then x squared is greater than 0. And then, end of proof. What's wrong is it didn't consider one of the cases. Remember the principle of trichotomy for real numbers. Every real number is either positive, negative, or 0. And it ignored what happened in the third case. For existence proofs, where you're trying to prove that some number exists, or some quantity exists, or some thing exists, there are 2 strategies. There are constructive proofs, where you show the thing exists by constructing and exhibiting it, and there are non-constructive proofs. And these you might use some theorem involving, say, the axiom of choice to demonstrate that something exists, even though you haven't shown how to find it. Here's a classic proof. Show that there are an infinite number of primes. How many prime numbers are there? Well, we're going to show that there can't be a finite number of them. There is an infinite number of them. This is an existence theorem in the sense that we're saying there exists an infinite number of primes. The method of proof uses proof by contradiction, reductio ad absurdum. We assume the opposite of what we're trying to show and show that that leads to a contradiction. Suppose there are finitely many primes. And in particular, we're going to name them P1, P2 through Pn. Suppose those are the entire set of primes right there, whatever they may be. What we're going to do is we're going to construct another number, we'll call it P, And we'll construct this by multiplying all of these primes and then adding 1 on top of that. Now, p, this number that we've constructed, is either prime or composite. If it is composite, then it could be expressed as the product of two other integers. And we'll assume we're in the set of natural numbers here. And we'll also assume that a and b are not 1. They're at least 2. If either a or b is prime, then one of these primes, which is our complete list, pk, will divide evenly. When you divide evenly into p, it has to have a remainder of 0 when you do the division. But when you divide p by any of these primes, you get a remainder of 1. It goes evenly into this part, but you have this 1 left over. You get a remainder of 1 whenever you divide this number by any of our finite list of primes, which means that neither a nor b is prime. That means none of our primes divides evenly into this, but every composite number can be expressed as a prime times something else, which means that p is not composite. That means p is prime. But if p is prime, then we have a contradiction, because we said we had a list of a finite number of primes, and then we found one more. So that's the end of the reductio ad absurdum proof, because we've shown that if there are finitely many primes, we can always construct one more. We're going to give you a non-constructive proof. Show that the equation x squared minus 2 equals 0 has a solution that lies between 1 and 2. We're going to use something called the intermediate value theorem. The intermediate value theorem says that if you have some continuous function on the interval ab, and if you have some intermediate value k, there has to be some point c in the domain where the height of the function at c is equal to the height k. And so we're going to set f of x to be x squared minus 2. This is a polynomial, and so it's continuous everywhere. And in particular, it's continuous on the interval from 1 to 2. What is f of 1? It's 1 squared minus 2, which is negative 1. And in particular, that's less than 0. What's f of 2? It's 2 squared minus 2, or 4 minus 2, 2, and that is greater than 0. So we have this situation. 1 and 2. At 1 we get a negative value. At 2 we get a positive value. 0 is the intermediate value. There has to be a place in between by the intermediate value theorem. there exists some point C between 1 and 2 such that f of c takes the intermediate value of 0. Now, the intermediate value theorem tells you that the point exists, but it doesn't tell you where it is. It just tells you it's somewhere in between the two endpoints. Let's look at uniqueness proofs. In particular, existence and uniqueness kinds of proofs. First of all, to show existence, you need to show that you have one. Then, for the uniqueness part, you suppose that there are two, and then through a valid argument you show that the two are in fact equal, and that shows that there is only one. So there is one and only one. That's the way uniqueness proofs almost always go. What is an additive inverse? Well, negative 2 is an additive inverse of 2 because 2 plus negative 2 is 0. If you have some x, y is an additive inverse if x plus y gives you 0. In our next example, we're going to show that every real number has a unique additive inverse. So we have and unique. That's existence and uniqueness. So the existence part is easy. Let x be a real number. We'll set y to be negative x, whatever that is. Then x plus y will be x plus negative x, and if you add a number to its opposite, you get 0. So every real number will have at least one additive inverse. Then we need to prove uniqueness. So this is the existence part of the proof. Now we need to prove the uniqueness part of the proof. So here we'll suppose y1 and y2 are additive inverses of x. What does that mean? That means 0 equals x plus y1 and 0 equals x plus y2. If we solve this equation for x, we get x is, moving this to the other side, minus y2. We'll plug that in over here and have 0 equals negative y2 plus y1. If we move this over now, we get y1 equals y2, and that shows that they aren't distinct. They are in fact equal. So if there are two, they're not different, they're the same. We're next going to look at a strategy where we reason from both ends to meet in the middle. So you work on both sides of something and try to meet in the middle, and then you can declare the end of the problem. So let's do an example. Show that if x and y are both positive and they're not the same, then the algebraic mean will be strictly greater than the geometric mean. This is the algebraic mean. This is the geometric mean. Let's rephrase what we're trying to show. Since x and y are positive, we'll get the same thing if we square both sides. When you square the right-hand side, it gets rid of the square root. The left-hand side will be x squared plus 2xy plus y squared divided by 4. So we're trying to prove this. If we can prove this, we can backtrack and arrive at the conclusion that we are seeking. We'll multiply 4 on both sides here, and let's move this over. If I have 2xy and I subtract 4xy, I get minus 2xy. So if I can prove this, then I'll be done. But this is a perfect square. It's x minus y squared. And that is bigger than 0 because x and y are distinct. We don't get 0 here. We'll get something non-zero. When you square something non-zero, you get a positive real number. And so now we'll work from this back to here, back to here, back to here, and then back to there. So we can reverse these steps and arrive at the conclusion that we seek. We're next going to look at reasoning by past ideas. In other words, reasoning by analogy with things that we did before successfully. And so let's look at the problem. Show that the square root of 3 is irrational. We already know that the square root of 2 is irrational. Hippasus of Metapontos showed us how to prove that. So we're going to reason in the same way. A reductio ad absurdum, a proof by contradiction. We'll suppose that it is rational, and then show that that leads to a contradiction. Suppose root 3 is rational. Then there exists p and q in the set of integers, q not 0, such that the square root of 3 is p divided by q. If you square both sides of this equation, you get 3 is p squared over q squared. Or in other words, p squared is 3 times q squared. This tells us that p squared is divisible by 3, and that implies p is divisible by 3. Divisible by 3. That means p is 3 times some integer k. If we plug that in up here, 3k squared will have to be equal to 3q squared, which implies that 9k squared is 3q squared. We can divide a 3 off and get q squared is 3 times k squared. That implies q squared is divisible by 3. It implies q is divisible by 3. But that means that our fraction wasn't reduced, and it's fair game to assume that the fraction is reduced, which means that p and q share no common factors. They've all been canceled out. But we've just shown p and q are both divisible by 3. That's a contradiction. So an assumption that we made is false. And in particular, the assumption that square root of 3 could be expressed as a ratio between two integers is the problem. And we deduce then, therefore, root 3 is irrational. It cannot be expressed as the ratio of two integers. Sometimes you spend a long time trying to prove something is true and you can't quite make the proof. Maybe the theorem is false. Maybe it's just not true. In which case, your time could be more productively spent looking for counterexamples. Here's a proposed conjecture. To repeat myself, suppose we assume that all primes are sums or differences of squares. We already did this for 2, 3, and 5. They check out. They are sums or differences of squares. Let's look at 7. Can 7 be expressed as the sum of 2 or the difference of 2 perfect squares? So 1 squared plus 2 squared is 5. 1 squared plus 3 squared is 10. That's already too big. 2 squared plus 2 squared is 8. That's too big. So there are no other real options here. What about subtractions? 8, 3, this is not even prime. Okay. A lot of these not prime. For the difference of squares hypothesis, maybe we could write this as x squared minus y squared and try to figure out some relationships about x and y. Note, however, this is x plus y times x minus y. And if we're going to have this be positive, x has to be bigger than y. Otherwise, we'll get a negative here and you won't get 7. You'll get something negative. So if x is bigger than y, and x and y are both integers, then x minus y is at least 1. So you have to work with x plus y less than or equal to 7. Then you'd go by exhaustion. After that, look at all positive integers, x bigger than y, so that x plus y adds up to something less than or equal to 7, and then you can test all possibilities. In all deductive sciences, there's a particular strategy for constructing the theory. You explore a bunch of possibilities. From your experience with all of that exploration, you can make a conjecture about some property. Once you have a conjecture, what's required is a proof. So remember these 3 steps: exploration, conjecture, and proof. Finally, some problems can be deceivingly difficult. A classic example would be Fermat's last theorem, which is pretty easy to state. If A, B, and C are, say, natural numbers, and n is a natural number strictly bigger than 2, so it's 3 or higher, and there are no such solutions to a simple equation, a to the n plus b to the n equals c to the n. We know that when n equals 2, there are many solutions to this equation. We call them Pythagorean triples, like 3, 4, and 5, etc., 5, 12, and 13. But when n is bigger than 2, say you're using cubes or powers of 4 and so on, then there just are no solutions. People searched for a proof to this for a very long time, about 200 years, before Andrew Wiles finally came up with a massive proof. It took him several hundred pages to come up with his proof. And even then, when he first presented his proof, there were some small holes in the proof yet to be filled, and he worked very diligently and finally overcame those struggles, able to prove Fermat's last theorem. But it's so easy to state, there are no integer solutions or natural number solutions to a simple equation like this when n is 3 or more. There is no general proof method, and there are many more methods besides what we've presented here. So, don't be too alarmed. Math is an ongoing constructive process. We get it bigger and bigger and bigger as you go out into the tree of mathematics, creating new terms and providing new theorems, and this will branch out forever. There's no end in sight to the possible number of theorems that can be proved in mathematics or in any other deductive science.